All right, chapter 5, our third chapter in our order of, well, not chapter 3, chapter 5. I said third and wrote 3. It's called polynomials. Poly is a prefix that means more than one. And nomials is a fancy word for numbers. So polynomials basically means more than one number, basically. So in this chapter, we're going to be talking about polynomials, but we're actually going to be talking about 4 different terms. We're going to talk about, there's our polynomial term. But if we use that understanding of these ones, monomial, binomial, and trinomial, if we know that nomials means number, then we could probably extrapolate the fact that monomial means one number, binomial means 2 numbers, trinomial means 3 numbers. That's pretty simple. Because mono, you know, from a monocle or that little thing the Monopoly guy doesn't wear, but we all think he does. It's a one little eyeglass piece. Mr. Peanut wears one. A bicycle is a form of locomotion with 2 tires. And a tricycle is a form of locomotion with 3 tires. So we all know mono, bi, and tri from our experiences with regular words. And poly simply means more than one. So the instructions say, for each expression, identify the number of terms and whether the expression is a monomial, a binomial, or a trinomial. Now, before we get to that, if we look at A, and this is 5j squared, we need to know first, before we start this, that algebraically speaking, I'm not going to put an equal sign. I want you to make a note here. So before we start question A, in fact, I'll draw A down here a little bit. I want you to get used to what these algebraic things are going to be. This is going to be an x or whatever type of variable we use. In the case of A, it could also mean a j, right? And if we don't shade it in, if we simply keep it open or white, we're going to consider this to be the opposite of whatever x is, or therefore we're going to consider it to be a negative value of x. Okay. So when we talk about our algebraic terms in terms of drawing, those are 2 you have used before. You have never used, however, this one. I don't think, or maybe you have. Have you guys used this? What is that going to be? A double x. Nope. If we think about where the x term gets its value, it actually gets it from its area. And what we're going to do is we're going to call the length here x and the length here 1. And therefore, the area of that particular algebra tile will therefore have an area of x. So really, when we define it as being x, we're really defining it as being the area. Here, still a length of x. Figuratively speaking, it has a imaginary width of -1, which is impossible. I get it, because you can't really have a negative area. But that would be it. So with that in mind, if the length here is the same length as here, and this is the same length as here, or not here, but the other one right here, then this is going to be an x by x, which is going to mean, what is that tile going to represent? Using our exponents laws now. That's going to be x squared. Correct. We're going to call that one x squared. And if we have it empty, without shading it in, that's going to be equal to, I'm running out of room, so I'm just going to write sideways, a negative x squared, the opposite of x squared. Okay? It simply represents the opposite of. And then we're also going to have just our grade 7 little, we're going to make this solid one a positive 1, and an open little square, we're going to make it a -1, right? And those are the 6 algebra tiles we're going to use within this chapter. Now, when I say x, it doesn't have to be x. It can be j, it can be k, it can be l, it can be z, it doesn't matter. So with that in mind, if I look at A, which is 5j squared, pictorially, this coefficient of 5 tells me how many of these I need to draw, right? So if a j squared or an x squared is represented with this, big mamma jamma, I'm going to drive 5 of them because the coefficient says I have 5 of them. 1, 2, 3, 4, 5. So the interesting thing is it says identify the number of terms. What do you think, without me telling you the answer right now, how many terms do you think that is? Anybody want to guess? How many terms do you think that is? What do you think? Carl says 1 or 5. Which one is it? How many say it's 1 term? That's what I'm asking you. How many terms? You don't know yet. If you're guessing, how many say it's 1 term? How many say it's 2 terms? Interesting. Okay, 2. How many say it's 5? The answer is it's 1 term. And a term is going to be, well, in order to define a term, here's how we're going to define it. I'm actually going to use, you can copy this down right from the book. I'm going to paste this in. Can I do it? Yes, I can. Look at that. Magic. Extend the page here. So we're, oh, for heaven's sake, come on now. Come on, Betty. A term is an expression, most of you are thinking expressions like happy, sad, formed from the product of numbers and or variables. So a term is going to be defined as an expression, you're writing this in your notes, from the product and or of numbers and or variables. So when we're talking about product, we're talking about multiplication. And when we think about 5j squared, is really the multiplication of 5 multiplied by j squared, or 1, 2. And really, because it's product, we just really want to know this 5, this coefficient of 5, or the 5 multiplied by j, is just telling us how many of these x squared or j squared tiles we have. It's kind of like saying, how many apples do you have? Well, I have 5 of them. So I would represent with a 5 apples, or if an apple was instead an algebraic term like j squared, I have 5j squareds. So this 5j squared is just 1 term. It's the product of the j squared by the coefficient of 5. And then they have another example here. It says 9x is a term representing the product of 9 coefficient and x variable. And then it says, keep in mind, a constant value such as 5 is also a term. So if I think about x, oh, that's not what I want, my highlighter. If I think about that 5j squared, we'll say, and then I say plus 2, right? Then I would say, well, the 5j squared is this picture here, the product of 5 and j squared. And then the 2 is just this 1, 2. So it's not the sum, and remember, sum is our vocabulary word, which means addition. So in this case, we have 1 term here, the 5j squared, and we have another one of a constant of 2. So what kind of would that be? Would that be a monomial, binomial, or trinomial? What do you think for that one? Yeah, it's a binomial. Good. So going back to our examples here, I'll erase all this because we have got a ton of stuff up here. If we look at the second one, B, 3 minus m squared. So if I wanted to draw that for B, I would draw a 3, which is a 1, a 2, and a 3. There's my 3. And a negative m squared, or a minus m squared, will be this x squared or m squared not shaded in. How many terms do we have? 2. So therefore, this would be called a binomial. We would refer to it as a binomial. We have a constant of 3, and we have a term, or an algebraic term, of a negative m squared. By the way, just as an aside, if it was 3 plus 2x, just different question, but let's just bear with me. What's the 3 called again algebraically from grade 7? Your constant. What's your coefficient in this particular case? 2. Right? Your constant is 3. Your coefficient is positive 2. So going back to this one, Your constant is 3. What is your coefficient here? Is it 1 or negative 1? Negative 1. And I know that because I drew it as it is a negative. This is a negative m squared algebra tile. So therefore, my coefficient is a negative 1, or the opposite of m squared. If I look at question C, I have an AB squared. It's one term. I have the difference or subtraction of a negative AB. And then I have a positive 1 constant. So C would be a trinomial. Just 3 terms. An AB squared, which I don't know why they would use an AB squared, because we don't like to combine 2 variables together. Doesn't matter, but it exists. And then D, the last one, we would have one term here, another term here, another term here, and another term here. So there's 4 terms there, so you can call it a quadnomial if you wanted to. But because we only go with monomial, binomial, trinomial, and polynomial, because it has more than 3, we're just going to call it a polynomial. But weirdly enough, a binomial and a trinomial, since more than 1 is what polynomial means, a polynomial can also be a binomial and a trinomial. Or a trinomial and a binomial can also be a polynomial. That one sucks, I know, I get it. So with that said, I want you to try and draw x plus 2 for a second. Just draw it using algebra tiles. It would be an x, and it would be a 2. And therefore, if I was to define what type of polynomial it is, you would say is it a trinomial? Because it has 3 pictures? No. It's a binomial. Because it has an x, and it has a 2. It has 2 terms. And generally speaking, the easiest way to say that is if you have addition signs or subtraction signs, since the product of terms, if we go back to our definition, back here, a term is an expression form for the product of numbers and variables. If we look at this one, the sum does not make a term. The sum connects terms. Sums connect terms. Or the difference, if it was subtraction, would be connecting terms. So with that said, if I put x cubed plus x squared minus x plus 5, if sums and differences connect terms together, there's a sum, there's a difference, there's a sum, then these are going to be our terms. How many terms do I have? I have 4. How would I define that using my vocabulary? It would be just called a polynomial. Okay. Now it gets a little bit more complex when we deal with these ones, and I don't like the book using these, but anyway. This is interesting because it's the product of an x to a y squared. Right? It's still a product. So how many terms would that be? If it's just products of variables, just 1, and therefore it would be a monomial. Difficult to draw, but by definition it's the product of just numbers or variables, therefore it's called a monomial term. If we look at our second show, it says model the following picture. So negative x squared. All right, negative x squared plus 4x minus 3. What type of, using our newfound vocabulary, what will we call that? A trinomial. It's a negative x squared term plus a 4x term minus a constant of 3, or a negative 3 constant. When we draw it, a negative x squared will be a big old empty square. A positive 4x, that's an x, so we'll have 4 of them. The coefficient of 4 tells us how many of those x's we have. And then our minus 3. If you want to use the old integer chips instead of the squares, that's fine. Here, this is a same thing as this back in our integer chip days. The only reason why we use it is because we want to attribute the length to be this matching up the same length as the x squared, because it's 1 and a 1, right? So that's how we draw it. And for B, what expression is shown by the algebra tile model here? Well, if we look at it, what's this tile right here? Gavin, what's that one? X squared, right? How many x squared tiles do we have? We have 2 of them. Where do you see another one? Just one. So I could write 1x squared if I wanted to show that I have one of them. But do we need to write a coefficient of 1? No. So instead of writing a coefficient of 1, I'm just going to write x squared. And then we have not 1, but 2, but 3 of those. How would I write that? Chloe, what would I write for that one? If I have 3 of those little green strips. Are they going to be 3 x squareds, or are they going to be 3 x's? What do you think? Is it going to be a positive 3x or a negative 3x? Right, because they're green. If they were not shaded in, if they were like this, those would be negative 3x. But because they're shaded in, it's a positive 3x. And then right here, just like if I did these, what would that be? Negative 4. Okay, and that's how we do it. All right. Let's try a couple more of those. Let's just practice one more. What if I gave you this? What would this one be? Brian, what would that say? 2x squared minus 3. Is that what you said? You're almost perfect. What's wrong with Brian? I mean, let's not get into that because we can go on for hours with that. But what's wrong with Brian's answer? Yeah. Right. If this was shaded in, Brian's answer would be correct. But because they're not shaded in, they are negative, and therefore the coefficient must be negative 2x squared. Good. Let's try another one. What about this one? Now again, I'm using integer chips. Technically, if I'm using the proper, I'd have to use these little squares with a little shaded in. But it's the same thing. What's this one say? Keep the order of the terms correct. What do you think? Hankinson, what do you think? Anyone want to try this one? Sophie, what do you think it says? No, I can't believe I'm saying this. Sophie is wrong. Keep the order of the terms. Go ahead. Good. 3, and this is minus 3x. So that picture would be 3 minus 3x. Now, if you said negative 3x plus 3, it's not wrong, but it's not what the picture says. It's the same value. Those are the same thing. But we want to keep the order of our terms correct.